Mm. Okay, so I'll just be starting because we are on a limited time. So welcome to Workshop Zero. I'm Min, and today, so our agenda would just be to be getting started with the pace because Jeff has recovered the what is pace part, and then we'll have some hands-on time with pace itself, and then there will be a brief intro to like what Slurm and Slurm jobs actually are. Um, so we'll get started with pace. So first, as Jeff said, you will need an SSH capable terminal. So that will be Windows PowerShell, Mac OS terminal, Linux terminal. And then we'll use those to SSH into the cluster that you'll be using today. So first of all, for everyone, we we had the Pace people create an account on the login ice node. So just log into the host using GT username at loginice.pace.gatech.edu. So for example, this is what you will want from your terminal. And then when you type in your GT password, um, do not be alarmed if nothing shows up. That's just for security. Just type in your password and press enter, and then it will successfully log in. If nothing if it works, yeah. And then if you're successfully logged in, you'll see a prompt like the following. So this thing, and then that means you're now in the login node of a cluster, which you can use to access files, write code, submit jobs, etc. And then for most people, it's probably easier to use SSH within an IDE because you don't really want to SSH onto the login node and have to use like a very basic text editor like Vim or Nano or something like that. So in order to use SSH with an IDE, the easiest that we found is using VS Code. Essentially, you can just install this extension from a VS Code extension store. And then this is extension store is there if no one knows. That's a correct extension name. And then once you've installed the extension, you will notice that at the bottom left, there will be like a broken link looking kind of thing. It's very small. But you can click on it. And then when you select connect to host, um, you can enter the host name and password as shown previously. So, for example, like a log example would be like this, and then you would log in as you've done before. And then now you should be able to open the folders icon to see the contents of a remote. Like there might be some loading stages because the VPN can be very slow, but yeah, you just need to wait. And then so yeah. So just let us know if you have any questions up to this point. Um, or has everyone already done
A
that
live
before?
demo of logging in.
Yeah.
I'll do a live demo here of logging in. Whoopsie daisy. I'm actually already logged in right now, but I'll log out real quick. This is what it looks like if you're
Yeah.
in.
So just follow along with that.
So I'm on a blank terminal here. I'm gonna put my GT username, and then this first part here, after that is the name of the login node. Edu. Hit enter. It'll just ask me for a password with just regular GT account password. You'll notice when I'm typing, nothing is showing up. That's fine. And then when you log in, it should look something like this. And it'll bring you to like your home directory. Well, you have a bunch of stuff. Um, yeah.
Yeah. So everyone just make sure that you're able to follow up until this step because the following workshop will sort of rely on you being able to log into the cluster.
The school require you to be logged onto the VPN. Oftentimes, if you're on Georgia Tech's network, like at your own or, you know, on campus using campus Wi-Fi, you might not need VPN. It's kind of like hit or miss whether that works or it doesn't work. But that's what it should look like if you're connected. And
To install the VPN, if you don't have it, you can just look up like, oh boy, like tech VPN download probably. Yeah. And then okay, well, yeah, it'll just take you to a download link at some point. But I think on Wi-Fi, I've never needed it. I've never needed the VPN while on Georgia Tech Wi-Fi.
Yeah.
So is everyone able to go up until Zach's step? Okay, I
If you
think
need any help at any point, just raise your hand, I'll come up and see if I can.
I think everyone is able to.
I'll show them the repository to make sure they can clone it, right? So the code.
Yeah, is it shown on this? Do we have it on the site?
Have it right here. So we have a little repository of just like a little thing to run on Pace. So if you want to like look up this link here. Or
Copy
is
and
there?
paste into Discord.
Yes, okay.
Discord is here.
Yeah. Um, okay. So if you want to go find that link there,
It's in the general channel of Discord.
and then just type git clone and paste the HTTPS link, not the actual URL link. I've already cloned, so I'm not going to press enter. But when you do that, it'll create this little folder here of all the code for the workshop today.
Everyone successful? Okay, I assume everyone could do it. And then, yeah. So let us start with learning about how the slog command, like the basic slog command sort of works. So what does this slog n1 n task per node and t1 hour seem to mean? N1 means you're allocating one node. A node in this case doesn't necessarily have like a fixed meaning. Like it could be a processor or like it could be a machine, etc. inside the distributed computing world. But in this case, you just need to worry about, oh, I want to allocate one node. And then there will be 4 tasks that are running on that node. So those 4 tasks can be running in parallel. So for example, if you want to run like something like a matrix multiplication in parallel, for example, you can allocate something such as like one node and 16 threads in that node, etc. And then T1 means like this job would run for 1 hour, and after 1 hour, this job will be forcibly stopped. So yeah, make sure that you always allocate the enough time so that you are able to complete the work you want to do, because you don't want to run it in the middle of something and then it just stops and then nothing is saved. But also don't make sure that you're not allocating for more time than you need, because sometimes that might lower your priority inside this scheduling, and we don't really want that as well. You can also get GPUs by passing in different flags. So these are 2 of the flags that will allocate GPUs. So you notice that the commands are actually like sort of different. This is GRES and this is GPUs. So this GRES flag, argument specifies the number of GPUs per node, while the GPU specifies the number of GPUs per job. So that means like the total number of GPUs can be larger than the number of nodes. And then so for example, if we want to get an NVIDIA H200, for example, we could use GRES GPU H201. So what this means is we are getting one H200 GPU per node. And we have also 2 tasks per node because normally whenever you want to allocate a GPU, you want to make sure that there is a thread that's available for the CPU, and then there's another one that's available for the GPU. And that's why normally you would want to have at least 2 tasks per node when you're allocating a GPU. And then for people who haven't really used Bash at all, so some Linux terminology is directories, which is basically folders on Mac and Windows. And then there's a file tree, which is like the hierarchical structure that Linux uses to organize its files and directory. It's like a tree, so that's why it's called a file tree. And then there's a absolute file path and a relative file path. So normally, when you use the absolute file path, you can essentially like navigate to any file within the system in the correct manner. Whereas when you use the relative file path, if you use certain file paths, you are only able to navigate to the correct file when like the file is within the root of the relative file path. So it's a position of file or directory that's relative to where you're located in the file tree. So when you're not sure, try to find the absolute file path and use that. So some Linux commands is you can print the current directory with pwd in case you ever lost track of where you are currently. And then you can use cd to change the directory of where you are. You can also use ls, and then you can use make dir touch, make dir to ls to list the contents of a directory, make dir to make a directory, and touch to create a file, and cat to view the file contents if you don't really care about editing at that point. And for all of these, you can use the absolute file path, I believe. Except for I think make dir and touch. For those, if you want to create like a file within a subfolder that hasn't already existed or something like that, you would want to make a directory first and then use that command in order to create the file. The same thing for make dir. So let us practice. We are going to practice with the git clone repo, like the GitHub repository that Zach has already cloned. So yeah.
All right. So the first thing we're going to do to actually like run anything is we're going to need to allocate an interactive process with the salloc command. So if you remember, that was salloc. And then, oh, also kind of an aside, but if you want to like figure out like what you can allocate to an extent, or like what is actually available on your system, you can go to like the ICE website. I think I have it here. Oh boy, if I could actually click it.
Drag that down.
There we go. Yeah, so on the ICE website, they have a list of like all of the resources here. So like the way you would read this is so each like row represents like one node. So like a node is sort of like an abstract thing, but like kind of like one kind of like contiguous like block of like compute units. For example, like it could have like a bunch of like one node could have like several GPUs, CPUs, whatever. And then a node just like contains all that in like one really easy to access like block where all like the memory is really well connected. So for example here, there's 30 nodes of this type, which have these dual Xeon CPUs, and they have 24 cores in them with 192 gigabytes of RAM memory in that node. If we look down here, there's 4 of these types of nodes with these 40 cores, and then they also have some GPUs here. And so you can kind of just look through and see kind of like what nodes are available, how many cores they have, what memory they have. So just to make sure you can like don't like over allocate and try and request something that doesn't actually exist on your system. Okay.
Also, if you want to see how you can kind of like format this in the SL command, just do SL dash L. Should show you the,
Oh, really?
yeah.
Oh, yeah. Those are just the arguments to run it.
Yeah, language.
Yeah. But so the main like portions of the salloc command is we have to specify how many nodes we want. So I'm just gonna request one node right now. And then we can do tasks, CPUs, and memory. So each task isn't really like is just like how many like actual processes we're gonna run at the same time. So how many different programs we want to have running. And then we can assign all of those tasks CPUs. So we can give each task like one CPU, two CPUs, etc. And then we can specify memory either for the entire node or per like task. So to specify the number of tasks, I'll say dash n tasks per node. I'll say we'll start off with 16. So I'm gonna have 16 programs running in parallel. Um, to specify number of CPUs, it's CPUs as per task, I think. I'll just give I'll give each process one CPU. And then if you remember when we look at the things, we had like almost like 200 gigabytes of memory. So I'll just say we'll give ourselves 120 gigabytes. That should be more than enough. Just make sure we have enough. If you don't provide these, it should give you like some default values, probably like one or like I think like 8 gigabytes of memory. Actually, I'm gonna just reduce this. We don't need that much memory. And so if we run this, it should create oopsie daisies. I think it's CPUs, right?
Yeah,
Yes.
you miss an S.
When we run this, we'll give us interactive session. And so now we're like in our interactive compute node. And so basically we have access to all of the 16 CPUs we requested on the one node. And one really handy thing to look around in the way like a lot of like the Slurm or like programs actually work is they like set a bunch of environment variables so like the programs know how many like tasks and stuff you have. So you can just read through those and see what's set by doing oopsie daisies. Help if I spelled that right. There we go. So when we actually created this like interactive session, basically the way our like programs know like how many resources we have allocated is all these like Slurm specific environment variables got set. So you can see we got 16 tasks per node. One node, yeah, one CPU per task. 16 processes, which is what we wanted because we have one process per task and there's 16 tasks. Our memory should be in here too, but yeah. So that's just how the actual programs like figure out like what to do basically. Was everyone able to get an interactive node? Anyone need help? Okay, cool. All right, I'm gonna go to the workshop. Whoops. So in here we just have this basic like matrix multiplication program. Oh, I went to, by the way, if you cloned in just like the basic directory you log into paste from, it should be in this path. Otherwise, just find like the workshop 0 path and go to the source directory. I'll give everyone a second to get there. But in here we just have this basic C file or C program that just multiplies like matrices in parallel. A file to make it, and then this is the batch script that I'll discuss later. So if you want to compile it, you can just type make, and then that should give us this executable called matmul there. And then the way on ICE, the way you actually like run stuff or the way you like tell it to run stuff in parallel is you use this command called srun. In other places, you might have seen like MPI run or something. This is sort of like an alias to that, but it's a bit more fancy. We can run our program. Size is equal to 512. Hopefully that'll work. Oh wait, we weren't supposed to put the argument there. When you're running it manually like that, you just 512. But this should be running the matrix multiplication. I don't know why it's taking so long, but
Did you optimize it?
yeah, I ran the same thing earlier today. Was everyone able to like compile the program okay? Excellent.
You pull the latest then?
Yeah.
The optimized.
Oh yeah. Even before it was unoptimized, like 512 shouldn't have taken that long. Was anyone able to actually like multiply their matrix? You were? Okay, so that's good. There's also another way to do it. You could just mix. Let me try this here. I also wrote some stuff into the make file to just like make it and run it in one go. So my thing's just completely frozen here, as you can see, but hopefully you said yours was multiplying, right? Okay. So it's not my code then. That's good.
That's pretty unusual. Like normally it doesn't freeze.
Well, um,
Did you? No packages.
no, it's because I'll just see stuff. It's already installed by default. If it was Python, you have to install stuff. Oh well, okay. Well, mine's just decided not to run, but so if I could actually run it, I could do like I could show you like running like different task amounts into speed up. But like if you run it on your own, you should be able to like if you request like 4 processes versus like 16 we have, you should be able to see a noticeable speed up because multiplying the matrix in parallel. All right, sweet. I'll talk about the batch file now, or so this thing here. So it's called basically. So obviously we made this like interactive terminal, and as you see when I ran my program, it just like I can't do anything else with the terminal, right? Because the program's just waiting to run. Especially so this is like really like bad for like long running jobs when you want to do other things. Um, so there's a way to like just like define a job in like with this S batch file or here, it's really just an SH file. And then you can just tell the supercomputer to go like run your job basically. So let's walk through this. It's basically like the same things we did in the select command, except you give it a job name. These are all the same things I did earlier, as you can see. You give it an estimate of the time it's going to take. And then, so after you define like what the salloc command basically does, you like give it instructions to like run your program. So I'm just saying like load the C libraries. This environment variable is the directory where we ran like to run this job. And then this is the command I'm actually going to run to launch the file. So this should be in your thing here. And to the way you run it, so you can see the job.sh there. You just type sbadge job.sh. It'll submit the job. If you ls, it'll create these 2 new files here, error and out. And this is just kind of like a live view of like, because obviously like the program's not running in this terminal. So these files give you like a live view of like everything that the program is printing out to standard out or to standard error there. And also if you want to monitor it, there's this command called sq. And if you type it here, yeah. So then you can see your job. So we can see, here's the job I submitted. I called it matmul extra large. So you see the name there. It's currently running. It's been running for 24 seconds. It's using 1 node. It's using this node. And so we can see if it's actually finished yet by just so it hasn't started doing anything yet, but hopefully it'll finish soon. It takes like a minute when I ran it earlier today, but so yeah, and then if like your scripts like a lot of time like your programs have like actual output, so you can just like create like folders and like file stuff normally, and that'll appear here when like the job's running. And then this way you can also just run like multiple jobs at once and have them like all scheduled up. Obviously, when I ran SQ, my job immediately started running. That won't always be the case. Sometimes you'll have to wait in the queue to get started. But yeah, anyone have any questions? Anything not work? Did anyone try running the job script that got it to work? Alrighty. Well, I'll try that one more time running, but that's all I had. Let me know if you have any questions. Do you have more of the slideshow?
Yeah.
Okay.
Um, yeah, so this is what we just did. And then Zach already covered a bit about some Slurm like submitting Slurm jobs. But I will just give a brief intro like about what Slurm sort of is. So what it is it's a free and open source job scheduler for Linux and Unix kernels. So it is also the workload manager used by like most of the top 500 supercomputers, and that's why it's so famous. Unlike maybe other job schedulers that are more that are not open source and not free. So there are also commercial job schedulers that are that cost a bit, such as Google uses their own job scheduler in the industry, etc. But why is like a job scheduler necessary? So say that you're inside a house and you have like a computer. You know reasonably because like of what the other person is doing. Um, like maybe both of them are doing very light workloads. In that case, you sort of can safely just assume that splitting the CPU and the memory usage by half for each and then allocating both of them to each one is a very fair way to share the resources. And then if one of them is doing a very light workload, another one is doing a very heavy workload, you would sort of also split the CPU and the RAM in a way that the person who's doing the heavy workload will use most of a computer while the other person will just use like maybe just like 1% of it or something like that. So this is because you're all living under the house, sharing one single computer, that you're able to do this in a pretty reasonably fair manner. Just manually, partitioning computer resources. Let's say that you are sharing like a computer resource with a bunch of other people. Every single person has their own needs and wants. And also, like another problem is that it's not just a single computer anymore. It's actually a bunch of computers, a bunch of computers grouped together. Some of them have like a large CPU, small RAM. Some of them have a CPU, a GPU, and a RAM. There's like all different kinds of configurations, different kinds of generations between the CPU and memory. And you can see like it in this case, it is a lot more unreasonable to say like try to partition it according to like what everyone wants. Like maybe everyone will request a GPU even though it's not necessarily what they need. Um, in that case, this is when a job scheduler comes into place. It can allocate variable duration, exclusive and non-exclusive access to limited computing resources as efficiently as possible. So say, for example, someone allocate like wants a GPU, even though they don't really need a GPU, like the program doesn't run with a GPU. Like in this case, sure, Slurm will say, I will allocate you a GPU. But in this case, you will be sharing that GPU with another person. And you will not know that because Slurm will always manage it for you. Um, so what this does is ensures fairness and arbitrating contention for resources by managing a queue of pending jobs and running jobs, etc. And then this also provides a framework for starting, executing, and monitoring work for the cloud, for maybe the data center administrators. So everything up to now, you've been using Slurm to allocate interactive nodes. And it's the same thing that you've allocated using SBatch, which is sort of um, what it is talking here. This is a slide about like, yeah, what you can do using Slurm jobs. You can submit a batch file just like what Zach said, using SBatch. Use SQ to check all the non-completed jobs under your username. And you can also use cancel to cancel a submitted job, in case like maybe the job script is wrong or something like that. Yeah. So take home challenge, I guess, is you can try to do everything you did today by submitting your program as a Slurm job instead, or maybe do something in your coursework trying to do that. Not sure if anyone of you have coursework involved this Slurm. And yeah, this is a company that created Slurm, so respect to them. And there's also some useful resources if you want to learn more about GT Pace. And then if you want to learn more about job schedulers, specifically Slurm, there's a lot more that goes into it aside from what we have talked about and what most people talked about. So if you're interested in something like operating systems, distributed computing, this resource might be interesting for you. And this is like a list of upcoming events that we have. So February 22nd, there will be the Intro to GPU and CUDA Programming Workshop. And then February 24th, there will be the data center tour. And then March 3rd, there will be a Georgia Tech HPC faculty panel on applications. So this would be something where HPC is used, such as physics, like astrophysics, compute simulations, etc. We would have professors coming in talking about the research and how HPC has helped them along their journey in academia. So the first two will require sign up. We will send out the sign up link as soon as possible. The first workshop will actually provide you with an extra week of working with a GPU and working on pace. So that would be a very good opportunity in case like you don't really have experience with that kind of thing and you want to gain experience in that. Data center tour, that would just be very interesting to see like what an actual supercomputing data center looks like. It's really cool. And then yeah, HPC faculty panel, you'll get to know more about research and potentially even try to talk to faculty of your own, try to network and try to get your own research opportunities. Yeah, this is the QR code again. If you haven't filled it out, please fill it out. It's very helpful for us. And yeah, let us know if you have any questions. And that's it for today.